mentor in space technology. So let us give a round of applause to Mr. Nitin Sharma. Thank you.
Thank you, Sita, for your kind introduction. So, actually, we all know that space missions have always pushed the boundaries of science, engineering, technology, and human imagination. So we would see what are the advanced material for space science. Control. Before entering into the field of materials, first of all, we will see where India stands in the space science and technology. Actually, Indian space program stands for the among the remarkable stories which are related to science and technology. Actually, this is not a story of only rocket and satellites. The Indian space program is a testament of modern science, technology, their innovation and preservance, which we have done for last 50-60 years. Actually, our program initially started in 1963 when we launched some sounding rockets at Tumba near Trivandrum, which is actually, fortunately, the magnetic equator of the Earth is passing through Tumba. It is the southernmost point of the India near Kanyakumari, Trivandrum. So there, our visionary Dr. Vikram Sarabhai, who is also known as the father of Indian space program, he started the exploration of space science and technology in India in Tumba in 1963. And he convinced Indian government to make ISRO. In 1969, ISRO was formed. After that, we made our first satellite, which is known as Aryabhatta. After that, we started making rockets also. The SLV-3 was our first successful rocket. After that, PSLV, GSLV, GSLV Mark 3. Now we are making human-rated launch vehicles. So the journey is very long. Apart from the Earth's orbit, we have also crossed the gravity of Earth and we have reached to the Moon and Mars. Now we are planning to reach Venus also. So what are the roles of Indian space program? Because it is not just technological innovation, we are also giving some societal impact, strategic contributions, innovations, and economic and the global influence. We are also providing a platform for Indian talent to remain in India and serve in India without compromising in technology and innovation. So the Indian space economy, so we can see that currently when we discuss about the space valuation, we are just 1 to 1.5% out of the global valuation, but we are planning that by 2047, we will cover 15% global valuations coverage in the field of space. Now, as per Indian government's policy, that's a new space policy, along with ISRO, we have in-space, NSEAL industries and new startups also. Like earlier, only lesser than 50 startups in 2020, but now in 2025, there are more than 400 startups who have started working in the space technology. So, okay. These are the major centers of ISRO where we are working. Actually, this one of the major centers is in Ahmedabad. This is Space Application Center where we are making payloads for satellite. And the other center have also some their expertise role. VSSC is making launch vehicles. Then Satish Dhawan Space Center, we all may have heard that we are launching our rockets from that spaceport. So this is the journey of Indian rockets. We started in using SLV-3 in 1979. In that, the payload capacity was only 45 kg. Now we have reached to the payload capacity of 4.5 tons. So we have jumped about 100 times. So this is the improvement in Indian space science. So before entering into the materials, we would like to see what are the launch vehicles and satellites. in which these advanced materials are being used. The launch vehicle is nothing but it's a multi-stage rocket. We are using multiple stages which have different type of fuels. Some are solid rockets, then liquid rockets and cryo rockets. And at the top of the launch vehicle, satellite is placed in the payload fairing. So when a rocket progresses, it leaves behind the part whose fuel is already burnt. So ultimately, we reach into orbit where satellite remains. So now, okay, here students are not more, but when we go among students, they ask about the difference between rocket and airplane, rocket and missiles. So there is a basic difference in space and aerospace. In aerospace, the airplanes uses the oxygen of the atmosphere as a oxidizer to burn their fuel. But we don't have this luxury in rockets. So we carry fuel as well as oxidizer with us in rockets. And obviously there is difference in the application of rocket and aeroplane. Similarly, there is also difference in rocket and missile. Actually, basically same in case of rocket and missiles, but the purpose is different. So after rockets, we will see what are the spacecrafts. Spacecrafts are nothing but satellites. Like we have natural satellite who orbits Earth, that is Moon, but we have man-made satellites also, thousands of satellites which are placed in the orbit by not only ISRO, NASA, other space agencies also throughout the world. So basically, we place satellites in three orbits: LEO, MEO, and GEO. Low Earth orbit, middle Earth orbit, and geostationary Earth orbit. These are orbits of Earth. Then we also have transition orbits that carries the interplanetary missions. But we are just seeing the three main orbits. Those are LEO, MEO, and GEO. So we can see that in the low Earth orbit, the resolution of the camera would be very high, but the swath or the coverage area would be less. But in case of GEO, the coverage we can cover half of the Earth at a single time. So wherever communication is required, we use GEO orbit because we can cover the complete India or the complete continent at a single time. But whenever we require remote sensing, Earth observation, or any camera technology, then we use LEO orbit. And for navigation satellites, we use MEO, middle Earth orbit. So these are applications of some of Indian satellites. These are series of Indian satellites we all know. So this is the anatomy of satellite. Bus actually carries power system, propulsion system, thermal control system, electronics and units, then communication system, and the main part which satellite carries is the payload, which contains the mission specific instruments and equipments. Fortunately in Ahmedabad, in Space Application Center, we are making payloads only. So the payloads may be the camera and spectrometer and the communication areas, transponders and scientific instruments which we carry to Moon and Mars. So materials used for space missions. So we will come to the materials. So these are the basic properties which we require to select a material for any space mission. So these are generic properties but specific to space. So these are few categories of the materials. In fact, advanced materials which we are using in space currently. So the advanced alloys of aluminum, iron, titanium, magnesium, then super alloys, nickel and cobalt based, refractory materials also, and special purpose materials made for space only, then thermal protection system, the composite materials, the nanomaterials, other advanced materials like MEMS, shape memory alloys, metamaterials, and many more. So first of all, we will see the advanced alloys. So actually, these are not the generic alloys which we are using in day-to-day life. These are not SS304 or like that. Alloys are not capable to survive in the space environment. So we have made special alloys of ferrous also, which we use in our launch vehicles, making the rocket motor casings. One of the best alloy is margin steel, which has been developed by India indigenously in 40 to 50 years back. So And from aluminum point of also, we are using specific alloys which are developed for space only. So these are some examples. Then titanium is also a luxury for space science. Actually, this seminar is for composites, so I am not giving details of the metallic materials and alloys. So like that, magnesium is a very good alloy because it has a low density. So specific modulation strength are higher than the aluminum, but it has some constraints because its machinability is very poor. It is very hazardous. So, but ISRO has developed some technologies to machine it. Now the turn is of super alloys. These are nickel-based alloys. In Cornell, we must have heard that can be used in high temperatures. We are using in nozzles of the some of the our rockets. Then refractory materials, obviously these materials can survive high temperatures. So, okay, there are some examples of refractory materials are shown here. So then there are special purpose materials which we have developed for space technology only. Actually, powder metallurgy was not in use earlier, but when space science came into picture in 1950s and 60s, then powder metallurgy also evolved basically for space technology. Then after that, it was used in the general practice also. Then the soft magnetic materials are also the byproducts of the space science. Then bimetallic materials where the two sides of a same component are facing different environments, we use bimetallic materials. Then the electronic ceramics like dielectric materials, specially developed for space science, we are using in our ISRO missions. Now, thermal protection materials, we must have heard about the Columbia. The disaster happened in 2003, I think. That our Kalpana Chawla was there, that Columbia space shuttle could not survive during re-entry. The problem was that during launch, one foam particle collided with the space shuttle during launch, and the minor crack happened, but the team thought that the crack is very minor and the shuttle will survive during re-entry, but it proved wrong, and there was a disaster, and nobody could survive among those astronauts. So here we can see the difference in the temperature when we use the thermal protection material. The outer side temperature is 1700 degrees centigrade, but inside the temperature is only 130 degrees centigrade. So this is the difference the thermal protection materials are making in the space shuttles during the re-entry. Then only the metals or the other materials by using which the space shuttle has been made can survive up to 130 degrees centigrade, but they cannot survive at 1700 degrees centigrade. But this insulation is the crucial for this technology. For that, carbon, silica tiles, silica aerogels, flexible, reusable surface insulation, then ultralight, high performance sea foam. So all these materials have been made only for space. There are other uses of these materials, obviously. Now we come to composite materials. So this, along with humankind, materials also have been evolved. So starting from stone age, then bronze, iron, steel, silicon age, carbon age. Now we are living composite age. So that's composite R&D point of view, the NASA initiated R&D in composite in 1960s, and we are not far behind. We started our R&D in composites in 1970s. At that time, our one center of composite development was created in Trivandrum, known as Replace, Reinforced Plastic Center. The name was Replace, and ultimately composite replaced most of the metals. So the name has proven right. So I will not go into the definition of the composite material, the properties of composite materials. So these are various combinations which we are using in ISRO, different types of reinforcement and their metrics. So the why we use composite in space, ultimately that they're lightweight and they can survive the space environment. So why? Okay, then okay, that we have already seen. So composites are used in satellite in these components. What are the benefits? We already know that reduced launch cost, increased payload capacity, enhanced efficiency, and improved performance. In panel discussion, Ulkesh rightly projected that the cost of launching 1 kg of the payload is almost $25,000. That is in LEO. If we go beyond MEO, GEO, or interplanetary missions, the cost is very high. So composites are helping us to reduce that cost. Either we can reduce cost, or with same cost, we can launch more number of payloads. for instruments. So, okay, obviously the composites are cost effective, we have already seen. So this is the space environment which any material has to face in that space, particular space mission. There are ultra high vacuum, extreme high to extreme low temperature, solar winds, then various types of radiation exposure is also there, UV rays, X-rays, gamma rays, beta rays, etc. So yes, parts can withstand the harsh conditions. The major advantage of composites, they are tailorable. We can tailor them to for that particular property so that they can withstand this type of environment. That yes, composites can be exposed to high radiation. There are specific resins and epoxies those can survive in ultra high radiations. Thermal management point of view, composites are helping in spacecrafts and space shuttles and launch vehicles. The lifespan of the LEO orbit satellites is around 7 to 10 years, and in GEO it is 10 to 15 years. So the composites, we use two types of properties: the beginning of life BOL properties and EOL end of life properties. And we have seen in our design as well as practically that even using end of life properties, composites survive in the space and do all the function regularly, properly. Okay, it's obvious that composites are customizable. It is their biggest strength. They are highly tolerable. So composites parts are manufactured. That manufacturing technology we all know that, but mainly we are in SAC and ISRO we are mainly using layup molding, autoclave curing for making the composite parts. So when how they stand among the metallic materials, we can see that weight point of view, the least density the composites have, but thermally they are more stable. Stiffness and strength point of view, they have higher strength and stiffness than most of the metals. So most of our parts are made of the sandwich structures in satellites and payloads. And we also can control the tolerance on the composite parts. If we don't control the tolerance, then we will get 100 to 200 micron accuracy, but we control by some specific process after composite manufacturing, then we can get up to 20-30 micron tolerance also on composite products. So these are some case studies of the spacecrafts worldwide which are using enormously composite materials in their missions. So I will not go into details. Like that, these are the launch vehicles made by the Lockheed Martin, Boeing, Airbus, SpaceX, etc. All those are using composite material in launch vehicle also. So the scope of research I will not cover because in afternoon session, my colleague Prashant will deliver about the challenge and about there. Now, nanomaterials. The nanomaterials actually are the wonder of carbon atom. The carbon atom is very wonderful element. It can bond. It can make bonds with any element like silicon, oxygen, iron, zirconium. With every element it can make bonds. So these are allotropes of carbon, basically graphene, graphite, diamond, and buckyball. So the beauty of carbon is that it can make by making bond with itself, we can make a softer or lubricant material like graphite, and it can also make the hardest material of the world, the diamond, and the strongest material, that is graphene. The same carbon making bond with itself and making softer to hardest material in the world. So these properties we are utilizing in our space science also. So we are using nanomaterial, graphene. That is the planar part of the carbon nanomaterial. Then there are obviously difference between graphene and graphite. We will not go into details. These are applications of graphene in spacecraft. Then CNT also. Then we roll the graphene in a cylindrical form. Then CNT can be made. So CNT, if we play with the chirality of the CNT, we can make the same material as semiconductor or metal. So we can play with the properties of CNTs. So these are applications of CNTs in our spacecraft. There is much more scope of R&D in this field. So the other advanced materials, these are MEMS. This is multidisciplinary material, we can say. Then these are applications of MEMS. Then these are metamaterials. Also, these actually in the property of material, but we are changing the texture of the material. You must have heard about the blue morphed butterfly. it does not have any pigment or blue color, but because of the morphing of its wings, we see it as blue. These are applications of metamaterial in spacecrafts. Actually, as earlier told, that there are spin-off of space technology in case of material science also. All these materials have been developed because of the space science and technology. So this is a memory foam which we are using regularly in our mattresses in home. This is made of the memory foam. A few years back, I told this technology about this technology to my child. So one day he was oversleeping. So I told him that, please, beta, you have to go to school. But he told that, oh, no, Papa, I am not oversleeping. I am just testing the space technology using this memory foam. Okay, this now, okay, that as sir told that I am secretary of the SSME. So this is a society of earlier it was limited to mechanical engineers only, but now any engineer, any technologist who works to related any field related to space science and technology can join this society. Directly or indirectly involved in any technology which is related to space science. It may be student, it may be any corporate or industry, or individual who wants to become life member. So we regularly conduct many activities, and we have dedicated a website also, ssmeindia.org, to anybody who wants to join SSME. And